I'm going to begin by telling you a bit about what we're doing, trying to find planets around other stars. I'm going to explain why, in particular, I'm focusing on these small stars, what is so special about them compared to stars like the Sun, and in the end, I might leave you with the impression that, after all, maybe we're not alone. I should say up front that the work I've been doing has been figuring out how many planets there are in the galaxy that have the potential to be good environments for life. We have not found any life elsewhere, but we're trying to find good habitats for life that is similar to life on Earth. To begin, as many of you know, we're looking very hard to try to find planets orbiting other stars. So when you go outside on a clear night, you're looking up at the night sky, and you pick a star, maybe that star. You'd like to find out whether that particular star has a planet around it. In an ideal world, what you could do is take a snapshot and perhaps see planets orbiting the star. But in actuality, many planets are actually very faint compared to the star. So this is a tricky proposition. In fact, if you were to try to take an actual image of a planet orbiting a star, that would be like trying to image a firefly right next to a searchlight. So we can't do this in most cases. We have to rely on indirect ways to find planets. That means that we often detect planets around a star by noticing that as the planet orbits the star gets a little dimmer every once in a while if the planet crosses in front of the star. Or maybe we look at the star and realize that every once in a while the light is a little bit redder or a little bit bluer. Just as if you stand on the sidewalk and an ambulance drives by, you hear the sound of the ambulance change depending on where it is. I don't have time today to talk about all of these planet detection methods, but there was a wonderful lecture last month about the NASA Kepler mission, and I encourage all of you to check it out online on the Public Observing Night website to learn more about how the Kepler mission finds planets and their discoveries. To move on to habitable planets, when you think of trying to find life on other worlds, the picture that Hollywood leaves you with is this. Life that looks an awful lot like humans wearing disguises and perhaps maybe some funny noses and funny ears. But at the end of the day, these aliens look a little bit too human-like for the comfort of most scientists. So when we're talking about trying to find life on other worlds, we generally aren't thinking about trying to find things like Spock and Doctor Who. We're trying to find things like these microbes. These might seem small and unimportant, but all of these creatures have influenced the atmosphere of the Earth in some unique way. As life exists on a planet, it's using resources and then producing waste, and all of those chemical reactions and metabolic reactions actually change the organism's environment. So if we were looking at another copy of the Earth from our Earth, and we had very good technology, we could figure out that there was life on the Earth. To do that, we would need to be able to distinguish between things that microbes did and things that geology did. And that's something we're working very hard at doing right now. You might recall learning about methane on Mars and the controversies about whether that was due to volcanoes or to microorganisms. As it turned out, the methane disappeared, so the argument for microbes also disappeared, but that's a fun thing to think about for future studies of other planets. Speaking of planets, astronomers have done a great job trying to find them. This is a snapshot from the popular webcomic XKCD. This shows 786 planets, all to scale. So each of those circles is a different planet, with the larger circles representing larger planets and the smaller circles representing smaller planets. And before you start counting the number of planets, I should point out that this is already out of date. This figure should now be increased to include many more planets, and there's the possibility of including thousands of new planets from the NASA Kepler mission. Many of those discoveries haven't yet been confirmed, so there's a tiny chance that some of them could be something that looks like a planet that isn't really a planet. But in the end, we expect that once the Kepler data has been finally analyzed to its full potential, that we'll have something like 3,000 planets known in our galaxy. That's a big step up from 9 planets, or 8 planets, depending on who you ask. Looking at this figure, if you look very closely, there's a box right there in the center. All of the planets in our solar system are in that box. The two big brown dots in that box are Jupiter and Saturn. If you look closely at the rest of the figure, you'll see that Jupiter and Saturn don't look so big when compared to the rest of these planets. Many of the worlds we found elsewhere in the Milky Way galaxy are much larger. Looking back at that box showing our solar system, you can see two blue dots. Those are Uranus and Neptune. There are a bunch of Uranus and Neptune-sized objects in this figure as well. But there aren't that many objects that are the size of Earth, or even smaller. The reason for that is that it's very hard to find small planets. If you're an astronomer trying to find a planet around a particular star, your ability to detect that planet depends on how much the planet influences the star. If you have a tiny planet like the Earth trying to push around a big star like the Sun, that planet is not going to be very successful, so you're going to need a really sensitive instrument to try to find that planet. But if you have something like Jupiter orbiting a star like the Sun, that's going to produce a much larger signal, so you'll be able to find it more easily. And that's why, when you look at this figure, you see many more big dots than little dots. I mentioned the Kepler mission briefly, and I just wanted to point out again that Kepler has done a fantastic job teaching us about those little planets. The reason why is that Kepler is incredibly sensitive to trying to find small signals. The Kepler mission lasted for 4 years and gave us the incredible wealth of data. You can see here in this plot of the number of planets found of different sizes just how important the Kepler mission has been for changing our picture of planets orbiting other stars. The largest peak in this diagram is right over this blue dot for Neptune. So we have over 1,000 planets found by Kepler that are about the same size as Neptune. We also have 200 objects the size of Jupiter and 81 objects that are a little bit bigger than Jupiter. That fall off here, where you have fewer Jupiters than Neptunes, is real. On the other side, though, where we only have 351 Earth-sized planets, that doesn't mean that the Earths are less common. That just means that they're harder to find. If we actually correct for the fact that it's harder to find a little planet than it is to find a large planet, we end up with this plot, which was made by Center for Astrophysics scientist Francois Frassen. Francois corrected for how hard it is to find an Earth around a star, and he found that when he made that correction, he was able to plot up on the left side the fraction of stars that have a planet of a given size versus the size of the planet on the bottom. The leftmost column shows that 1 out of every 6 stars has a planet the size of the Earth. That's a lot of Earth-sized planets. And it's very exciting if you're trying to think about the number of planets in the Milky Way galaxy that could possibly support life. To answer that question, though, we need to think about more than just the size of a planet. We need to figure out what exactly makes a planet habitable. And if we do that, we can then answer the question, how common are habitable planets? Is it really just only the Earth in the entire Milky Way galaxy? Or is it something more like this, where the Milky Way galaxy is filled to the brim with possible habitats for life? In order to answer the question, we need a definition of a habitable planet. There are many different ways to think about habitability, but the one that appeals to me most is to try to think about a habitable planet that we could figure out was habitable without actually having to travel there. In our own solar system, we know that there could be water in the subsurface oceans of the icy moons of Jupiter and Saturn. But in order to detect that life, we would need to send probes to those moons. And that's hard to do in our own solar system, and with current technology, it's impossible to do in a distant solar system. So for now, astronomers tend to restrict their searches to planets that have liquid water on the surface. The reason for that is that we know that all life on Earth uses liquid water in some form or another. So we're going to infer that if we're trying to find life that we can recognize as life, maybe we should start with what we know and try to find life that does the same thing as life on Earth. In order to have liquid water on the surface of a planet, we have 2 requirements that we have to meet. The first is that we want to look for a rocky planet. We don't want to try to find something like Jupiter, because although Carl Sagan talked about the possibilities of having floaters in the atmospheres of Jupiter where maybe life could exist there, we don't know how we would detect that. So we're going to stick to try to find something that's rocky like Earth or maybe Mars. There's also a whole class of planets that doesn't exist in our solar system. Those are the things called super-Earths. They're intermediate in size between Earth and Neptune, and we're pretty sure that at least for objects that are less than about twice the size of Earth, they might be rocky, and those might be great places to look for life. Above about 2 times the size of Earth, we think planets are probably more like Neptune than they are like Earth. So that sets one criterion for us. We'd like to find a planet that's 2 times the size of the Earth or smaller. The second requirement for a habitable planet is we want something that's the right temperature for liquid water to exist on the surface. We don't want to find a planet that is as hot as Mercury, because then all the water would have evaporated. We also don't want to find something that's so cold that all of the water would be frozen. Now that we've established our 2 criteria, that we want something small and we want something the right temperature, we can look at the Kepler planet candidates and see if any of them match our criteria. I'm going to show you a plot now of all of the Kepler planet candidates. And the reason why they're candidates is because we still need to go through that final step of making sure that these are actually planets. But I'm going to promise you that 80 to 90% of these objects will end up being planets in the end. We're pretty sure about that because we know what sorts of false positives we expect to find. So what I'll show you is on the left side, how big is the planet compared to the Earth, and on the bottom, how far away is that planet from its star in units of the distance of Earth from the Sun. These are all of the planet candidates. It's a remarkable number of objects. You might be a little bit alarmed that there aren't any planet candidates below this purple line. The reason for that is that it's just very hard to find small planets in long orbital periods where they only cross in front of the star once every year or so. So we're not very complete in this region. Just the fact that there isn't anything there doesn't mean that there aren't really planets in that area. We just haven't looked long enough and hard enough to find them yet. If we zoom in on the area around the Earth, we can see that we actually have a couple planets that receive about the same amount of light from their star and are about the same size as the Earth. For comparison, this is where Venus and Mars fall on that plot. So you can see that these objects, at least in terms of their distance from the star, look a bit more like Venus than they do like Mars. But this isn't really a fair comparison because depending on how bright the star is, you might want to be a little bit closer or a little bit farther away in order to have a planet at the same temperature. It's just like turning up the heat on your gas stove. You can put your hand a little bit closer to the stove and still be comfortable if the heat's on low, but if it's on high, you pull your hand back. So in order to think about this on more equal footing for stars with different brightnesses, we like to talk about the concept of the habitable zone. This is our solar system, shown not to scale, with the rocky planets close in, the gas giants further out, and just for fun, you have Pluto on there as well. If we then figure out where we would like to live in this solar system, we could draw a green ring like this. And this habitable zone, also known as the Goldilocks zone, for the story of Goldilocks and Three Bears, is the distance from the star at which you could have liquid water on the surface of the planet. Anything inside that habitable zone, like Mercury and Venus, would be too hot to have liquid water. Anything outside, like Mars and Jupiter, would be too cold. In our solar system, you can see that this ring falls between the edges of Venus and Mars. And depending on who you ask and exactly which models you use for how planets respond to different amounts of sunlight, you might be able to push the outer edge out a little bit past Mars, or maybe inward a little bit past the orbit of Venus. But it's definitely going to encompass the Earth and surround either side of the Earth's orbit. Flipping the projection a bit and adopting a bit more optimistic range for the habitable zone, we can then ask the question, are there any other stars in our Milky Way galaxy that have systems like this? Systems where there are planets within the habitable zone? And the answer is really exciting. It's yes. And the reason why we know this is thanks to the Kepler mission and to ground-based radial velocity surveys, which is the way of finding a planet based on the Doppler wobble, where you see the light change color from red to blue as the planet orbits the star. And in that case, one of the examples of a planetary system with planets in the habitable zone is Kepler 62. This star has 2 planets, Kepler 62f and 62e, in the habitable zone. The planets are shown here to scale, so you can see that 62e and f are roughly 1.5 to 2 times the size of Earth. That's good. That means that there's a good chance that those planets are rocky. We haven't actually measured the masses of these objects, so we're not sure for certain, but there's a good chance. So maybe these would be good places to buy a second home. Who knows? One thing you might notice looking at this diagram is that it seems like the habitable zone for Kepler 62 is a little bit smaller and a little bit closer to the star than the habitable zone for the sun. That's actually true, and the reason why that occurs is because the star, Kepler 62, is cooler and redder than the sun. That means for a planet to get the same amount of light, it needs to be in a little bit closer. As it turns out, the majority of stars in our galaxy are actually small stars. On a dark night from Massachusetts, you might look up and see something like this. But if your eyes were very sensitive to red light, you would notice that there actually were 12 times as many red dwarfs as stars like the sun. You can see them filling in here in this animation. These red dwarfs are all over the place, and they actually annoy people who study galaxies so much that they refer to them as the vermin of the sky. But as someone who studies these red dwarfs, I prefer to think of them as the rubies of the sky. So they're really interesting stars because if you want to figure out how many planets there are in the galaxy that might be habitable, it makes sense to look around the most common type of star. And there are other advantages to trying to find planets around these red dwarfs as well. And that's just because they're so much smaller than a star like the sun. This is a diagram showing to scale the size of a medium-sized red dwarf compared to a star like the sun. Red dwarfs actually encompass a broad range of sizes. They range from about 10% to 60 or 70% the size of the sun, and they're much cooler. Because these stars are so much smaller, that means that it's a lot easier for a planet, even an Earth-sized planet, to boss them around. So if you have an Earth-sized planet orbiting an M-dwarf, you'll actually be able to see that signal from space or from the ground much more easily than you would if that same planet orbited a star like the sun. Another reason why I like to look for planets around these red dwarfs is that their habitable zones are much closer in. This is to scale the habitable zone of a sun-like star. If we throw up a red dwarf, though, you can see that the habitable zone is much, much closer in. In fact, a planet in the habitable zone of a star like the sun would have a year the same length as our year, 365 days. But a planet in the habitable zone of a red dwarf might have a year that lasted only 1 month. And that means if you're trying to find a planet around that star, you have 12 times as many opportunities to see the planet go around the star. And as someone who's trying to finish graduate school in a short amount of time, that's very, very helpful. So all of these reasons make the red dwarfs look like very attractive places to look for planets. But there's something else to consider, which is we live around a sun-like star, so we know a lot about what it's like to live around a sun-like star. But what would it be like to live around a red dwarf? Would things be different? Would it be irritating? Are there things about red dwarfs that make them good or bad places to live? And as it turns out, it's kind of a mixed bag. One of the things to notice about red dwarf planets is that they can sometimes be tidally locked. When we look up at the moon from Earth, we always see the same face of the moon. And for certain planets orbiting red dwarfs, the same face of the planet might always face the star. There are exceptions. You could have a planet that has other planets in the system, so maybe it would be in an orbit like Mercury's, where it's not quite the same face all the time, but it just rotates very slowly as it revolves around the star. Assuming, though, that you have one face of the planet always facing the star, which could happen for a large number of these habitable zone M-dwarf planets, then you would have to have serious discussions about where you'd like to live. Depending on the strength of winds on this planet, there might be one side of the planet that's very hot on the side facing the star, and the side away from the star might be very cold. In that case, it might be a good idea to live along the terminator, this line separating the light side and the dark side of the planet. But there's also a chance that the winds might be very strong along the terminator, so maybe you'd rather live somewhere on the day side. Of course, you could also change how much atmosphere the planet has. If it has a very thick, sluggish atmosphere that doesn't really have that many winds, the climate will be very different than a planet that has winds that are whipping around every day very quickly. So there's a lot of work now that's being done on modeling the climates of planets orbiting red dwarfs, and the results are encouraging. Early on, there were concerns that if you had a planet that was tidally locked to a red dwarf, all of the atmosphere would freeze out because the planet would be so cold on the dark side, and that planet would never be habitable. But now, because we have much better climate models that are able to handle all three dimensions at the same time, we now know that those planets could actually retain their atmospheres, which is very good news. Another thing to worry about if you have a planet in the habitable zone of a red dwarf is the fact that red dwarfs have a lot of flares, particularly when they're young. Can you imagine living on a planet and getting hit with this section of the star? That would be a major telecommunications failure. And for early life, that could actually be problematic if you have DNA or the equivalent of this alien organism's DNA getting damaged by ultraviolet radiation. But if you had a core of the planet that generated magnetic fields, perhaps you would have some protection against these dangerous flares. In addition, like people, red dwarfs calm down as they age. They go through a very rebellious youth. But once they get to about, maybe 1 billion years old, 10 billion years old, they calm down a lot. And then they actually become very mellow stars that are quite calm, predictable environments. Another advantage of living around a red dwarf is that they live essentially forever. This is a plot comparing the life expectancy of a planet in the habitable zone of a star like the Sun on the left, in that little yellow bar with a height of about 9 billion years, compared to the lifetime of a planet in the habitable zone of an M-dwarf, a red dwarf. In that case, this is 60 billion years. That's much longer than the age of the universe. There are red dwarfs that were born at the beginning of the universe that are still alive now. They haven't even reached middle age. The reason for that is that these stars are very small. They mix completely. They don't just use part of their fuel. They use everything that they're born with, and they use it at a very slow rate. They're really, if you think about it, the story of the tortoise and the hare, the M-dwarfs are definitely the tortoises. And they might win in the end, too. So that brings me to the next section of my talk, which is speaking more about the work that I did last year with Professor David Charbonneau, focusing on the planets orbiting the M-dwarfs in the Kepler sample. I'm going to show you now a plot of all of the M-dwarf planet candidates and talk about which of them might be good places to live. On the bottom, I'm going to show you how much light each of the planets receives. Here, the star is on the right side of the plot. So objects that are close to the star, like Mercury, would fall here at about 10 times the amount of light received by the Earth. Objects like Venus fall there. Earth-like objects get 1 times the amount of flux that the Earth receives. And then things like Mars would be on the left side of the plot. So things on the left side are planets that don't get that much light. Things on the right side get a lot of light because they're close to the star. On the left side, this is showing how big the planets are. So a true Earth analog would be right here. So watch that space and see if anything pops up. These are 95 planets orbiting Kepler M-dwarfs. And if I remove those color guides now and add in the habitable zone instead, you can see that we found that 3 of our 95 planets received the right amount of light to have liquid water on their surfaces. Of those 3 objects, 2 are very similar in size to the Earth, and 1 is just a little bit bigger than 1.5 times the size of Earth. So all 3 meet the criteria for things that are likely to be rocky and the right temperature to have liquid water. As part of our study, we looked at all of the red dwarfs in the Kepler sample. There are about 4,000 of them. And we figured out for each of those 4,000 stars how well did we look for planets? Would we have found a planet that was 2 Earth radii or 1 Earth radius, that went around the star once a month or once a year? And we were then able to figure out how we could convert our number of detected planets in the habitable zone into the fraction of stars that host potentially habitable planets. The number we found was that 15% of red dwarfs host Earth-like planets, where by Earth-like, we mean a planet that could potentially be habitable. Recently, Dave and I have been updating this calculation. We're using another 1.5 years of Kepler data, and we're also using updated boundaries for the habitable zone. We now have much better predictions for how far away planets can be from stars in order to have liquid water on the surface. When we add all of that together, our number increases from 15% to 50%, which is a number that I find very exciting because it means that 1 out of every 2 red dwarfs has a potentially habitable small planet. And there are lots of red dwarfs in the galaxy. A common topic when discussing the possibility of finding life elsewhere in the universe is the Drake equation. This equation is a way of estimating the number of intelligent, communicating civilizations. And depending on whether you think alien life is likely to be intelligent or interested in communicating with us, you can chop off the equation at whatever point you'd like. So to begin, Frank Drake estimated the number of stars in the galaxy. This is something that we can go out and measure fairly well. This is a known quantity. The next term in this equation is multiplying the number of stars by the fraction of those stars that have planets. Back in the 1960s, when the Drake equation was proposed, F sub p was completely unknown. We knew in our solar system that we have 1 star and that star has planets, so maybe it was 1. But maybe the sun was the only star with planets, so maybe it was a very small number. Now with Kepler, we know from François Frassen's results that 1 out of every 6 stars has an Earth-like planet. And it seems increasingly likely that nearly all stars have a planet of some sort. The next term in this equation is, for the stars that have planets, how many potentially habitable planets do those stars have? Is it rare for a star to have a potentially habitable planet, or is it very common? The next term is, given you have an abode for life, is there actually life on that planet? And then, if there's life there, is that life intelligent? What fraction of life actually becomes intelligent? And then what fraction of that life chooses to communicate with other civilizations? And the last term, which is the one that might be a little bit scary if you compare to the current state of humans on the Earth, is how long does that civilization actually manage to exist during the planet's lifetime? Is there a point in which civilizations become so intelligent and so smart that they immediately wipe themselves out? Or are they able to survive until the star itself dies? As an astronomer, I feel very comfortable with these 2 terms and perhaps the first 3 terms. But I really have no idea what values we should plug in for F sub L, I, C, and T. And I hope that in the future, biologists and chemists and astronomers can work together to come up with reasonable answers for things like the fraction of planets that have life on them and the fraction of planets that have intelligent life. But for now, I'm going to present you a red dwarf Drake equation in which we can estimate the number of potentially habitable planets orbiting red dwarfs in the galaxy. The first term in this equation is just the number of red dwarfs in the galaxy, which is something we know. The next term is the fraction of those red dwarfs that host potentially habitable planets. So from surveys of our neighborhood in the Milky Way galaxy, we know that there are 248 M-dwarfs within 30 light years. That's essentially taking the census of all of the planets, all of the stars that live on our block. We also know that something like 50% of those red dwarfs have potentially habitable planets. That means that we have about 120 potentially habitable planets in our neighborhood in the Milky Way galaxy. If you convert that to the distance that we would have to walk in order to go to the nearest potentially habitable planet, it works out to about 6 light years, which is a hard distance to think about in human terms. So to make things a bit easier, I'm going to take the Milky Way galaxy and scale it down so that the distance across the galaxy is the same as the distance across the United States. walking across the United States is still a very long journey, but it's something that's easier to think about than trying to walk across the galaxy. On that scale, we're going to go to Center for Astrophysics in this auditorium, which is where the star is. And if the Milky Way galaxy is the size of the United States, the distance we would need to walk is about 0.3 miles, which means that all we would need to do is walk from this room across the quad to the bike repair shop over here. So that's pretty close, and I would be very happy to walk that distance if it meant I got to see a potentially habitable planet. Which brings me to the next question, which is, how are we going to find these planets? Kepler was a fantastic mission, but the goal of the Kepler mission was to do statistics. So Kepler stared for a very long time at a very narrow region of the sky. We need something now that will look everywhere and find all of the nearest planets orbiting the brightest stars. That mission exists. It's called the Transiting Exoplanet Survey Satellite. This mission is managed by Harvard and MIT and will be launched in 2017. The goal of the TESS mission is to try to find planets that we can subsequently characterize. We want to generate a whole population of planets for which we can study each of those worlds in detail and figure out, does this particular world have signs of life on it or not? And if it does have signs of life on it, we'd like to keep on observing it so we can make sure that those signs of life are actually due to life and not due to some aspect of geology that we don't understand. So as a reminder, this is the Kepler field on the sky. It's about 100 square degrees. And this is the TESS field on the sky. It's pretty much the entire sky. There are these regions here, these stripes along the ecliptic plane where TESS will not look because TESS observes as strips. It has 4 cameras stacked up. Those 4 cameras will look at one section of the sky in the northern hemisphere for 1 month. Then they'll move over a bit and look at another section of the sky for a month, and then another section of the sky. So it's like peeling an orange or an apple, that if you have a straight peeler and you're trying to peel it, you're going to overlap near the top of the apple, and you'll have some gaps near the equator of the apple. Because of the way the strips overlap, TESS will end up looking at the fields near the poles, those regions in yellow, for over 100 days. So TESS will be able to find planets in the habitable zones of smaller stars, like those red dwarfs. Near the equator, though, TESS is only going to look for 27 days. In comparison, Kepler looked for 4 years. So we're probably not going to find a planet that is Earth-sized in the habitable zone of a star like the Sun with TESS, unless we get very, very lucky. But what we will find is a bunch of planets that are small, orbiting a variety of stars. And that means we can really try to understand what makes an Earth-like planet Earth-like, and what just means that it has really interesting geology. Once we find these planets with TESS, we're going to need to figure out how we're actually going to detect signs of life. One thing we could try is to imitate Jodie Foster from the movie Contact. Only we probably wouldn't put on headphones to use a radio telescope. Generally, you look at a computer screen instead. But this definitely makes for a better shot. There are people who are actually doing this. This is one example. This is the SETI Institute's Allen Telescope Array. This array is currently capable of detecting communications that are directly beamed at Earth, but they couldn't find things that are just stray communications. The next generation of radio telescopes will be able to pick up on leaked electromagnetic signals. So in that case, if another alien world is out there with the same pop culture as our pop culture, then this XKCD cartoon might be a good description of what we would hear from them. In the center here, we have the sun, and this is a diagram showing the kinds of things that the Earth has transmitted to the rest of the Milky Way galaxy over time. Because light travels at a finite speed, the civilizations, the planets closest to us, are more up to date. So if there's life on Alpha Centauri, they are being rickrolled right now, which is kind of terrible. But if there's life on Sirius, they're farther away, so they're a little bit behind the times, and they're kind of upset about Harry Potter. So this is definitely a funny figure, but it does drive home the point that if there are intelligent communicating civilizations out there, perhaps we're going to pick up on some of their bad reality TV programming in the distant future. In the meantime, though, there's probably less talkative life is probably the kind of life we're most likely to detect. So in that case, if we can't guarantee that there's some alien civilization out there with radio programming and television shows, how are we ever going to try to find them? One thing we could do is to pay very, very close attention when the planet crosses in front of the star. So here is a schematic showing a transiting planet, that dark disk crossing the surface of a star. As the planet crosses the star, if that planet has an atmosphere, which is the orange ring, some of the light from the star will pass through the planet's atmosphere. And anything in the planet's atmosphere, maybe oxygen or carbon dioxide, will leave a fingerprint on that light. And that means that we will be able to tell what's in the planet's atmosphere. Here's another way of looking at that. On the left, you have a star. The starlight is being transmitted through the atmosphere of the planet. And then an astronomer takes a prism, or a spectrograph, to split up that light into a rainbow. And this feature right here is due to something in the atmosphere of a planet. In this diagram, this is a sodium feature, but in the case of trying to find life, we might look for something different. We might look for signs of water, for instance. On Earth, we know that plants appear green to our eyes, so maybe we could try to look for signs of vegetation as a possible fingerprint for life. If we had infrared sensitive eyes, we would see that the plants are also very, very bright in infrared wavelengths. That's because plants reflect a lot of light at green wavelengths and infrared wavelengths. If we were then to construct a plot showing how bright plants look at different colors of light, we would be able to tell right here that there is a large jump where here we have green light and over here we have infrared light. And all of a sudden, things get much brighter, where the reflectivity jumps up. That feature is called the red edge, and it's due to vegetation. So we could try to look for that on other worlds. We could also try to look for this feature here, which is a bump in the reflectivity due to chlorophyll. This might seem a little bit Earth-specific, because how do we know that we would expect to see similar features on other planets? But it's a good starting point. And astronomers are working hard now with simulations to try to see what the Earth looks like at different times of year, assuming that you're looking at different portions of the Earth and that your instruments are varying levels of quality. Another thing you can do to test your ability to differentiate between worlds with life and worlds without life is to compare what you see in the atmosphere of the Earth to the atmospheres of other planets in our solar system. In this case, for the Earth, if you look at a plot of how bright the Earth appears to be versus the color of light, you can see little dips corresponding to ozone and water and carbon dioxide. However, if you were to make this plot for Venus, you would just see a dip for carbon dioxide. No ozone, no water. The same thing is true for Mars. So perhaps seeing the combination of water, ozone, and carbon dioxide tells you that there might be life on a particular planet. This requires lots of modeling to make sure that you're actually seeing a real signal that could only be explained by life instead of by a combination of other factors, but it's an active area of research. We need new instruments in order to get these data, though, for other planets. And there are a couple things on the horizon for how we're going to try to get these measurements for planets orbiting other stars. One of those missions is the James Webb Space Telescope. This instrument is being built right now and should be launched by the end of the decade. This is a scale model on the lower left, showing only a small fraction of the people who've actually helped with this mission. James Webb will be in space, and it has this big shield on the bottom to try to keep it cold, because it's going to do a very good job looking at the atmospheres of planets. James Webb will also teach us about other areas of astrophysics. Another area in which we'll be able to learn a lot more about small planets in the future is by using large telescopes on the ground. These large telescopes collect much more light than the current generation of telescopes. The current large telescopes used by professional astronomers are about 30 feet across. The next generation will be close to 100 feet across. It's a huge telescope. There are 3 possible designs for this next generation of telescopes. One of them is the 30-meter telescope. Another is the European Extremely Large Telescope. which is quite a creative name. Both of them are very creative. And my personal favorite is the Giant Magellan Telescope, which is the project that Harvard and the Smithsonian are helping to build. The reason why we want such a large telescope is that increasing the size of your telescope increases your ability to collect light, which means that you're better able to study things that are very small signals. In this case, one of these mirrors in the GMT is the size of a current cutting-edge large telescope. So this is an incredible improvement in our ability to measure the atmospheres of other planets. The Giant Magellan Telescope will also help us to find planets that are orbiting stars. Right now, it's shooting lasers off into the sky, which might seem very odd, but the reason why the GMT will do that is because if you're trying to look for very small signals, the fact that the atmosphere changes can be a problem. But if you shoot a laser up into a particular level of the atmosphere, where there's lots of sodium atoms, you can actually measure how the atmosphere is distorting the light that you see, because the laser will shoot up, hit something up there, and then bounce back down. And because you know what kind of signal you sent out, you can measure that you're then getting a fuzzy signal back, and you can correct the shape of your mirrors to compensate. So it's really remarkable technology. We have that available now in some large telescopes, but this is going to be a whole new regime when we have adaptive optics, which is what the laser system is called, operating on a 24-meter telescope. So to summarize, there are 3 main points from today's talk. One of them is that small planets are common. Prior to the advent of exoplanet detection, we really didn't know if that was true. All we knew about planets was the planets in our own solar system. We knew that we had rocky planets close to the star and gas giants farther out, and we had no idea whether this was common in the galaxy. The Earth might have been all alone, but now we know that most stars have planets. We also know that there are many potentially habitable planets in the solar neighborhood. We saw before that all we would need to do is walk across the quad to find the nearest potentially habitable planet, and that's a distance of 6 light years. The other thing I'd like you to remember from today's talk is that there are many interesting missions designed for the near future. Those missions will allow us to detect planets that are nearby orbiting bright stars. And with that population of planets, we're really going to be able to study them in detail and look for possible signs of life. I'd like to thank everybody who's been involved with this lecture series. And I also want to show you a video of what things would look like if all of the planets discovered by Kepler orbited a single star. This video was put together by Alex Parker, who's a scientist here. And we know that all of the Kepler planets orbit different stars, but this video is accurate in the sense that the planets are the sizes they should be, and the time it takes them to orbit the star is actually to scale. On the bottom here, you might be able to see the time elapsing in days. So right now we are 15 days in, so you're only seeing the very close-in planets. And as the video continues, we're going to move out, and you'll be able to see planets that orbit farther and farther away from their stars, more like the Earth's orbit around the sun. And thank you very much for your attention, and my apologies for the microphone problems.